electronics, but how to measure electronics. So we use electronics in a lot of stuff, and if anything goes wrong, you're going to have to measure. So we're going to do what we call a common measurements today. This is a thing on common circuit symbols. You also have to learn how to read electronics. Reading electronics is like reading music. You just have to learn how to read it. Okay? So here you see the abbreviations. Previously we talked about sizes. You've got to learn today, you've got to learn sizes in math or whatever. So again, easy way to 10 to the 6th power is what? Anybody? 1 million. What? So that's where we were in our generation, but that's not where we're at now. Now we're down to things so small, we couldn't see them a few years ago. So anyway, go here. And you're down to 10 to the minus 6. Obviously, electronics and engineering, that gets very, very complicated. So in the computers, they have what they call math, the floating decimal point, where you float your decimal point depending on what you want to talk about. You want the computer to work down here at nanometers, picometers, micrometers, milliliters. You float the decimal point down because you don't want to rework with 0.000000010. So if you look there at the abbreviations, let's start with the we don't have the one. It's interesting. But anyway, let's start with the kilogram. Kilogram, kilo, whatever, is 1,000. Then you go up to the 1 million, that's 10 to the 6th power, and that's a mega whatever. Now, it don't really work up there. If you're driving your car, you will, but we're going to go down today into this minute world. Yeah.
What's the significance of the X?
Of what?
Of the X. So you've got an X.
Times.
Okay.
So, what that means is if you got 2 million, it's 2 times that number.
Oh, okay.
If you got 4 million, you got $4 million
Okay.
for the bail bond that was set last.
Yeah. That got changed, by the way.
I give her credit.
Yeah, I do too.
I like Claudia. Okay, so anyway, let's go down rather than up. And down, 0.001 is millimeter. Okay? And that's a little m. And then the Greek letter, okay, is a micro. And that's 0.00001. Nano is what we're going to work with today, and we worked somewhat in the past with nano. Okay, N. And that is what?
8 zeros.
That's basically 10 to the minus 6. 1 million below the top. And then if you get lower down, you got the pico.
I want to ask a question.
Yeah.
You used the expression 10 to the minus 6 when you were talking about the nanos.
Right.
I don't understand 10 to the minus 6.
Well, you know what 10 to the 6 is? 10, 100, 1,000. Right?
No, I haven't got it yet.
10 to the 6th power. 1,
Okay,
2,
to the,
3,
but
4, 5, 6.
what are you multiplying? What's the power?
10 times 1
Okay,
10 times 2, 10
Okay.
times 3, 10 times 4. 10, I'm sorry, I'm thinking about binary now, 2. This is 10 times 10. 10 times 10 is 100.
Okay,
100
okay.
times 10 is
Okay.
1,000. 1,000
Okay.
times 10 is 10,000.
okay, thank you.
So but you do that same thing, but you're going down the other way.
Okay,
Got it?
okay, yeah.
Okay. Okay, then your abbreviations for micrometer become relatively important. Well, let's go over Ohm's law. We talked about Ohm's law. See Ohm's law there? Here's a basic. Volt equals I times R. Volts equal I times R. Current, resistance. Current, resistance. Volts. We talked before about what is resistance. The easiest way to think about it is a tank of water. You have a tank of water, gravity pushes down on that, you put a pipe in there, and the water is going to come out the pipe. Depending how big the pipe is, how short it is, depends on how much water is going to come out. You put a faucet on there, open it and close it, that's your resistance. Open it halfway, you got half the resistance. Open it all the way, different resistance, right? Close it, complete resistance. So that's what you're going to measure. And trying to think. The only other one that's important that we probably won't talk about a lot today is watts. Okay. Watts is another measurement. If you're going to buy something, if you buy a sound system or speakers, it'll say it's 1,500 watts. 1,500 watts is a lot louder than 550 watts, 500 watts. So, okay, here you got this for ohm, V for volt, I for current, A for amps. Let's move on to the equation of what you're going to be measuring and why you measure it. And by the way, I'm no electrician. I'm a doctor, so this is what you have to learn to get into medical school, and then you'll learn all the time you're in medicine, because just like everything here is electrical, the whole body is electrical. Anyway, here you got a battery. Okay. So we got lots of batteries here today, and then you make an electrical circuit. So your battery can be 1.5 volt or 9 volt, depending on if it's AA or a D battery or AA, it's going to have a certain number of volts. Then up here, you have resistance. So the resistance is anything that holds back electricity. Okay. The opposite of resistance is conductivity. Anything that conducts electricity. We conduct electricity with what? Wires, copper, various kinds of wires. Some that are better than others, and so on. So, anyway, here's your equation. So they've got down here 20 volts, and the resistance is 10. So they want to know, in this example, I equals E over R. over R. 20 over 10, and that equals what?
2.
2 amps. So volts, okay, E is volts. So if you're measuring something now, which we're going to in just a little bit, we'll measure some resistors. Okay, the other thing, we'll get into a lot, the complexities, but there's another law called Kirchhoff's law, where all of the electricity theoretically has to be used up. If it's not used up, if you get too much to the LED that we're going to talk about, LED, what's going to happen? It's going to pop. It'll blow out. So if you get more here, let's say we're going to get the LED. And then the LED only takes 1, okay? And you've got 20 coming through, you're going to have to make sure that there doesn't get any more than it can handle. So if it can handle 1 plus 1, let's say, plus or minus 1, that means this is 2 or 3, and then your resistor would have to take out what? 17 volts. Or this is going to pop or not be good. So everything does have a plus or minus. In other words, a range. We'll talk a little bit about ranges. Okay, let's look at this one. We talked about before specifications. You really have to learn how to read specifications, and hopefully you will if you're going to buy something. You've got to make sure what you're buying is going to do what you want it to, so you have to have specifications first, and then buy according to that. Or in the world of electronics, if you're making stuff, everybody puts out what they call a data sheet. And on that data sheet will give you all the information you need to know. For example, on the most things electronic, if it goes over 130 degrees, it ain't gonna work. If it goes down to minus 10 degrees below zero, it probably won't work. All that'll be on the data sheet. So that kind of tells you. Don't use it if you're gonna go skiing. Now, some cameras you can use, but you have to make sure if you buy it to, obviously if you're gonna buy it to go diving under the water, you've gotta make sure it's waterproof, right? So it's the same thing related to the weather, all the specs, and so on. So these are called the LEDs. And we've got here red, green, yellow, white, and blue. We've gone over some electricity before. We'll go over a little bit now when we talk about the electromagnetic spectrum. But anyway, the head diameter, you want to know how big it is. If it's 3 millimeters or 5, you've got to drill the hole for it. Like on your TV set, almost anything we buy today has got an LED on there to tell you it's turned off. It's red. You click the button, it's going to turn on, it's usually blue. So that LED has to be able to change colors or have different LEDs in there. The voltage for white is 3.2 to 3.4 volts. If you want it green, 3.0 to 3.2. Blue, 3.2 to 3.4. Red, 2 to 2.2. So it's lower for red. Okay. So that's your volts, the V. Your current is 20 milliamps. Amps. This is part here. So if you give it too much voltage or too much power, again, you're going to burn it out. So look at the next one. That shows you some of the burnout things. This sheet here. Here, if you look down at the bottom chart first, it's got your NM. That's nanometers. nanometers. You got green, 565 nanometers. The voltage that put through to light that thing should be 2.2 to 3.0. Let's go to the red, 690 nanometers. That's 2.2 to 3.0 nanometers. Now go to the charts above there, light output. Again, it's got your nanometers, 300 to 900. This is more or less what the eye can see, from 400 to about 700. And then as you see, somewhere in here it talks about the infrared. Here, 400, 900, 940, you get into infrared that you can't see, but these diodes can see. That's why you can have a camera that will show you what this room looks like with the lights on, infrared. So go down to the next one, and it shows you the forward voltage in the current in milliamps. Shows you the voltage between 0 and 3, and the milliamp current between 200 and 220. You see, if you push it too hard, if you push it over, what? 80 milliamps or 3 volts, it's going to pop, won't burn out. Hopefully it won't pop. Pop is dangerous. Okay, next one is light output. Light output is more or less linear 2 milliamps. The more milliamps you push to it, the lighter it's going to be.